Today we'll be talking about nDPI. That is the cornerstone of many nTop applications, but that is not known by many people. Let's go deep on their subject. What are the problems that we want to solve? First of all, we need to monitor traffic. We need to interpret traffic that's passing in our network. And depending on who you are, the type of analysis you can do on the traffic is different. For instance, for internet service providers, you have the problem of DDoS. That is the problem number one, to make sure that your infrastructure does not collapse. And you need to understand how the traffic is moving inside your network. But in general, the traffic that these people are moving is not the traffic. It is traffic that somehow is passing through the network, but it is not belonging to them. And then you have, for instance, a hosting provider, so somebody that, or a standard company, so somebody that has a different type of problem. So in essence, they are providing services. The network is used by users to carry on a certain job. The traffic is originated, terminated into their network, and they need to make sure that everything is in order. So in this case, you can do DPI, so you can inspect packets. So it's a different type of scenario. But in both cases, you need to interpret traffic, because even if you're an IXP, you want to know how much traffic, for instance, is going to Google Mail instead of Google Search. And this is one of the basic things that we need to solve today for visibility. Because visibility is the problem number one today. So this means that depending on who you are, on the fact whether you own the traffic that is passing through your network or not, you can apply different type of monitoring. If you own the traffic, you probably have the ability of looking at packets. So to understand the nature of the communications by looking at the packet payload, and use tools some similar to, for instance, Wireshark, where you can capture the traffic and you can go deep. If you are an IXP, capturing is only for troubleshooting, and most of the time you don't capture anything, but it's the network itself that is delivering you the data that you need to have in order to understand the nature of the communications. This means that many times it's a network device, either a switch or a router, that is delivering you the information in terms of S-flow or net flow. Many times net flow is the preferred path because it is running on the router where the traffic is passing. So we have the problem of visibility. But in both cases, we need DPI. In one case, for example, in IXP, you need to interpret the traffic according to the DPI rules, limiting it to the packet header, to what the flow is reporting. If instead you have the ability of looking at the full packet content, then you have the ability of going deep into the packet. So what is, in essence, is DPI? DPI is the ability of inspecting packet payload. So therefore, if you don't have packet, you don't have DPI. This is a simple equation. But as I've said, we need to do some sort of analysis of the traffic, even though you don't have the ability of looking at the packet payload. So therefore, over the years, we have enhanced the initial DPI concept where P stands for packet, even to non-packet environment. One of the problems that we have is that the network speed is always increasing, okay? And many DPI libraries are expensive. We heard that sometimes the price of the library depends on the yearly revenues of a company that is using it, or on the cost of the application. So therefore, it's a percentage. And in many cases, this is making DPI very expensive, okay? And this was one of the reasons why we started to look at this problem, to understand the traffic nature, but from a different perspective, to have something that is not expensive, but that is actually free, okay? Because today we'll be talking about nDPI that is open source, and also that is easy to monitor. And the requirements in 2025 are full visibility, so to understand in case you have packets of what is happening on the network, in case you have packet headers or flows, to have somehow a rough idea of what is happening, and of course to have ETA, that stands for encrypted traffic analysis. It means that even though the traffic is encrypted, we need to figure out what is happening on this traffic, okay, not to understand the communication itself, to see what people are exchanging, because this is not the scope of our toolkit, but to understand whether this traffic is acceptable from the network standpoint. if it doesn't include any, let's say, encryption issues that we'll be talking about later in this presentation. nDPI started, as a fork of a popular, at that time, library called OpenDPI that was unmaintained, and we wanted to create a DPI toolkit, but we said, hey, why don't we start with this toolkit? And we started at nTop to play with it. Okay, the library had several problems. It was basically a prototype, okay, a proof of concept, I would say. And we have over the years, because this story started about 2013, more than 10 years ago, the library had several limitations, also several performance problems and memory problems. So we have solved, I don't want to say all of them, but let's say the library today is in good shape. We have added many protocols. Now we have about 450 protocols. We have added the ability of extracting metadata. So not just to see what is happening on the network, but also to characterize the data, extracting data that is meaningful for monitoring. So for instance, the URL, just to tell you something familiar, or if you have a DNS communication, the host name that is being queried. And also we have added some cybersecurity feature we'll be describing later. So in essence, today, DPI in the nDPI parlance means to understand what is happening on a network, to exploit as much as possible packets if they are available. If they're not available, to try to have an idea of what is happening on the network, even though we don't have packets. So in this case, the detection will be not 100% precise, but it will be good enough to have a rough idea of the traffic. And we have added many algorithms into this library because the library needs them. Just to tell you a couple of them, when we have to monitor networks, we need to face with IP addresses. And so playing with IP addresses is something pretty common. Okay, so we have, for instance, the ability of understanding and playing with IP addresses to know whether a certain IP belongs to a certain network, and if it belongs to a certain network, then it's probably of a certain protocol. So we have implemented all those features, or we have implemented the efficient substring matching that is used by nDPI to match, for instance, host names or eventually URLs, for instance, for malware detection. And nDPI is available on GitHub, so you will see the link here at the bottom of this slide, as LGPL version 3, free and for everybody. In nDPI, the main idea, okay, is to detect protocols. So it means that we have to characterize a certain traffic, encrypted or not encrypted, doesn't matter, into two things: major and minor protocol, or if you wish, major and application protocol. And the major protocol is basically the network protocol used on top of IP. Okay, it means, for instance, in this case, so we have DNS, or we have QUIC or TLS, if you're familiar with this type of traffic, that is sitting right on top of the IP protocol. And these are real protocols that are described on an RFC, protocols that are known to everybody most of the times. And then we have the application protocol, in this case, a YouTube upload. In this case, the term protocol is probably misleading, because this one is not a real protocol that is documented. Sometimes it is, sometimes it is not. So in this case, YouTube upload, we have no clue what is happening inside this protocol, even though we imagine that it will be a sort of probably HTTPS upload or something. In this case, protocol is characterizing the application, is characterizing the intent of the person that is using the protocol. So in this case, this person wants to upload a video to YouTube. Okay, and why we need this distinction? Because there are some protocols, so for instance, YouTube, that can run on top of TLS and on top of QUIC, but the protocol per se is the same. Okay, it's just the underlying transport that is different. That for many people is a detail. Okay, so you know that, for instance, we are now moving from TLS to QUIC in many applications, and the fact that this is happening is not very relevant for most people. People want to understand, or network administrators want to understand whether people are watching YouTube or doing something different, right? They don't care too much about the major protocol underneath. And many times we hear questions such as, how many application protocols do you support in nDPI? And we say, well, about 450. And some people say, hey, but toolkit X asked over 2,000, over 3,000. This is not a good question, I would say. Okay, first of all, because as you will see later in this presentation, you can define your own protocols very easily. So therefore, if you have a configuration file, you can say, you know, this protocol 1, 2, 3, 4, whatever. Okay, you can specify very easily cnn.com as a protocol, as many other toolkit seem to do. This is not what we want to do. In general, for us, protocol means something meaningful, something such as TLS, such as Quick, okay? And those application protocols that are created based as derivative of existing protocols can be configured on a config file. So you can have as many protocols as you want. At the moment, I think we are limited to 65,000, but in general, this is not the right question. Also because many people don't know what is a protocol about. So they just want to know categories, okay? We'll be talking about that in a second. If you go to GitHub, okay, if you are a developer, this is what you will see on your screen. So in essence, we have under SRC, most of the source code of nDPI as a library. And then here in example, you have an example application called nDPI Reader that is used for us to test the features of the library and to do regression testing and many other things, and also to showcase what the library is doing. Inside the same directory, there's also a simple application, simple integration is called, that allows you to see how to integrate nDPI in your application. nDPI is written in C, okay, plain C code. And then we have other components. So for instance, at the bottom, you will see Wireshark. That is a directory that contains extensions, nDPI extensions that are used inside the Wireshark. So for instance, from Wireshark, you can see the application protocol of a certain communication. You can extract metadata, or even eventually, you can extract information about flow risks code. So something that is meaningful from the cybersecurity standpoint. And one of the things that make us very proud is the testing, because nDPI is a library on top of which your application will be sitting on. This means that the library must be stable, or rock solid, I would say, and it has to be, very, very good from the memory footprint. And whenever we do something, we add a new protocol, we change something, we must make sure that the regression tests are not failing. And for this reason, at the end of this presentation, we'll explain you how this happens. But enough you to know that we have fuzzy testing. So the library is constantly fuzzed against random input or semi-random input, just to make sure that we don't fail. And also we have several other tests that are executed whenever we commit code to the GitHub repository. Dissection works in steps. In essence, we divide the sectors into big families, those for TCP and those for UDP. Again, nDPI starts on top of IP. So it means that non-IP traffic is really not relevant for DPI. Okay, so whenever we have an IP packet, the packet is passed to nDPI. I will show you later the API, and is classified. And we need to divide the traffic in something called flows. So it means that we need to sort packets according to a communication, the usual 5 type of communication. So packets belonging to the same source IP, destination IP, source port, destination port, and to the same protocol. This is called flow, similar to what NetFlow defines it. And based on the flow, we apply dissectors. As I've said, we have about 450 protocols, so we have more or less this number of dissectors. And of course, we need to start from the dissector that is most likely to match the traffic. If you see, UDP port 53, you will start with, for instance, DNS. That it makes sense. And then if it doesn't match, you will go with another dissector, but all dissector for UDP, because this is a UDP flow. If instead it's a TCP flow, you will start with TCP flows. And in essence, this is an iterative process. And if you are lucky, we can stop with the first dissector. If you are unlucky, we have to go through all the dissectors. And then when we have no dissector that's matching the traffic, we have to mark this traffic as unknown. And the fact that we have unknown traffic is not bad per se, but it's somehow annoying because the user would like to know about everything. But especially today with encrypted traffic, is a nice code to have, but in practice it is probably a bit complicated. It's challenging. but we are doing our best to reduce the unknown traffic, because this is the idea of the application. Another option for stopping with the dissection is when we have applied so many dissectors to the traffic that we say, I give up, because we already spent too much time on the traffic, and we simply stop here, and we label this traffic as unknown. This means that nDPI is applied at the beginning of a flow, when the initial flow negotiation is observed. So, for instance, if you have a TLS flow or another type of flow, at the beginning there is meaningful information that is exchanged, that is used, for instance, to detect a certain protocol type or a certain service. So, for instance, at the beginning of this talk, I said Google Mail versus Google Search. Okay, this is the right time to do the matching. So therefore, nDPI is applied only at the beginning of a flow. So therefore, even if nDPI is adding a little performance overhead, because in addition to what the application has to do, we need to process the traffic inside nDPI, the overhead is limited to the first few packets. But then we have creative ways of reducing that. You will see in a second. The way dissectors are working is pretty simple. So in essence, a dissector will register here at the bottom a function saying, call me this callback nDPI search headers.io whenever you see traffic on IPv4 or IPv6 UDP with payload. So it means that if we have traffic without payload, so for instance, a SYN packet, just to give an idea, or a UDP packet without any content, or if we see traffic that is not UDP, don't even involve this dissector, because this is not relevant. Inside the dissector, these are a very simple dissector, and it's not, they are not all simple as this. Inside this dissector, you will see that we do some checks. Okay, if we believe that this traffic is the protocol we're searching, we call nDPI set detected protocol. If we believe this traffic is not meaningful for this dissector, we say exclude dissector. These two things tell to the nDPI engine that we are done. So in case here we have detected the protocol, or in the latter case, this protocol is not for sure headers.io. So therefore, move to the next dissector and don't consider this dissector for this flow anymore, because this one will not match. So this is the way it works. It's an iterative process, but as I've said, we will be starting always from the first dissector that is most likely to match. So this is the very important thing. And if you look at how code is coded, so how users of the nDPI are using the library, they have to do an initialization. Okay, you do this one per thread. Okay, because it's very important to avoid the locks inside nDPI. So if you have multiple threads, initialize the library one per thread, and every thread will process traffic without going into locks. The main function is nDPI detection process packet. Okay, to which we pass the packet at the IP header. So it's a task of the application to decode the packet up to the IP. So if there are some encapsulation, if there are some MPLS header, VLAN, this is something that the application should strip, and then pass the packet to the nDPI. nDPI in return returns a protocol ID that can be unknown, okay, or can be whatever the protocol, okay. So in case, so we have not detected the protocol, but we have spent too much time with this flow, then we call something called give up. Okay, give up says, okay, I don't know what else to do with this flow. So nDPI try to guess what is the application based on the information that I passed you, and then give up returns you an application process protocol. Okay, and then of course at the end you will end with the detection. Now, if you're wondering what is the overhead introduced by nDPI, there is not a simple answer, because it depends very much on the traffic, okay? Because every traffic is different. For instance, there are some flows such as UDP, TCP flows that are easy to guess, others that are complicated. So for instance, a typical example is DNS. With DNS, one packet is enough, okay? So if you have something more complicated, such as a TLS communication, then you have to wait for a few packets until you make a decision. So the nDPI reader application that is part of the examples directory shows you at the beginning when you started some statistics. So in this case, you will see that in average with this pickup I've tested, we need about 5 packets or almost 2 packets for UDP. So as you can see, UDP is faster to detect than TCP, but in general, these are the packets that you need per, let's say, per protocol, per layer 4 protocol. So therefore, it looks to me pretty reasonable, okay? It is not a lot. It means that in addition to what your existing application is doing, you have to pay this little overhead at the beginning of the flow just to identify flows that are, need to be dissected by nDPI. That to me looks not very much. If you look in terms of memory or CPU, basically the CPU cost is proportional to the number of packets that you need to have for dissecting a flow, right? But in terms of memory, so we have to pay 2 costs. One is the cost of the library, of the initialization of the library, that you pay once, okay? So in this case, it's about 3 kilobytes. And then you have to pay a certain overhead per flow, because nDPI has to keep a sort of story, okay, or cache, let's say, for a flow, where it can store metadata. So for instance, the URL, or additional information for remembering up to what stage, okay, a certain flow has been processed, or for detecting, for instance, what dissector have to be applied, or what dissector have not matched, so therefore should not be considered at all. So in this case, you pay an overhead of a little bit more than 1 kilobyte. Now, this number changes according to the protocol, because for instance, if you have HTTP, you have very long usernames, very long user agents, very long URLs, okay, this one will increase. If you have other protocols, probably this memory will be reduced, but you have to pay an overhead, okay? Later, I will show you how to avoid that. Now, there is not a rule of thumb, but in general, this is the memory in average that you need per flow. And also remember that as soon as nDPI is over, and as I've shown you before, the amount of packets that you have to process is very limited. So we have seen before that it was about 5 point something packets per TCP flow, or a bit almost 2 for UDP. You can free this memory. So this is a temporary memory that you need to have during a flow dissection. And in addition to dissecting protocols looking at the payload, you can also do sometimes a different type of dissection based on other attributes. So for instance, in this case, based on the username, or sorry, on the host name. So in this example, for instance, the Xbox, that the popular protocol used by Xbox devices, can be detected looking at the host name. The host name is present in protocols such as HTTP or TLS, for instance, and nDPI extracts the name and is matching this against the protocol. Or another thing we do is to match a certificate. So for instance, the popular AnyDesk, okay, remote sharing protocol, is detected because it's TLS, okay, from random IPs, because apparently this company has various sites around the world. So therefore, we cannot really detect it with an IP address. We cannot detect it with the host name because there is no host name. In fact, in TLS, the host name is optional. But we detect it, for instance, using the certificate, okay, the TLS certificate. In other cases, we specify the IP addresses. In this case, it's for Cloudflare Warp. The IP addresses that we put on a file are either defined by the company that is releasing the product. So for instance, Microsoft is reporting the IP addresses of Office 365 servers. So whenever we see a traffic for a certain host that has been reported by Microsoft as Office 365 server, so we know for sure that we don't have to go deep into the packet, because this is going to be Office 365. And this is very important for NetFlow, or for environments where we have no packet access, okay? Because this is the only way, it's one of the few ways, let's say, that we have to understand what is the protocol. In other cases, it's going to be the last resort in case we have a packet analysis, whenever no dissector is matched. So for instance, a flow was already in progress when we have started our nDPI application, so therefore we had no chance to see the initial flow bytes. Inside nDPI, in addition to protocols, we also have the categories. A category is a way to cluster together applications in groups, okay? At the moment, we have about 120 categories. And categories, from my point of view, are more relevant than protocols, because many times people say, I want to stop peer-to-peer. I want to block traffic in groups, okay? And I challenge you that not all of you, even today, or myself, don't know all the peer-to-peer protocols, but it's easy to say block peer-to-peer because nDPI, when registered for the protocols, knows the category. Knowing the category, you can do in one shot, okay, what you could do in adding various protocols, that is very more, let's say, I would say it's more complicated. Also, if you use the category, you also have the ability of whenever we had a new protocol that is a peer-to-peer, okay, to have the application updated. Otherwise, if we had a new protocol that is a peer-to-peer, you don't know that this was a peer-to-peer protocol. If you don't select this as a protocol, you will not match it under peer-to-peer. So therefore, I encourage you to use category a lot because they are very helpful, in particular for configuring applications. In addition to that, we have protocol breeds. Breeds is another, let's say, way to classify traffic, but for a different purpose. So for instance, a category means, let me go back. Category means, for instance, the family of the protocol. Is this email? Is this a database? Is this a remote access? It doesn't say a lot about the nature of the traffic. With breeds, here we specify whether the traffic somehow is acceptable, for instance, or not. If it's funny traffic, so you're watching a movie, or if it's dangerous or potentially dangerous, such as, for instance, Tor or other type of hidden VPNs that are used by many people to circumvent the rules. So a breed is another perspective on the traffic. Okay, if for every protocol you have both of them, okay, and depending on what you're doing, you can use one or the other, or even both of them at the same time. In addition to that, nDPI is extracting some metadata. And the metadata information is extracted depending on how you use the library. So if you need to characterize the protocol, because if you need to figure out what is the application protocol, and that's it, okay, probably you don't need metadata at all. Instead, if you want to have a rich monitoring application, you need to extract metadata as much as possible. So for instance, if you want to block traffic that is not supposed to run on your net, for example, fun traffic, let's say YouTube movies, okay? If you want to block it, you don't care what type of host you're accessing or what too much detailed information about this traffic, right? You just want to stop it. So as soon as you see, you decide that this is YouTube, you have to block it. So the metadata extraction will be limited simply because in the iterative process of passing packets to the library, you will be stopping earlier. Instead, if you want to have a full report, you have to pass to nDPI as much packets as possible. And then, of course, nDPI says, that's enough for me. I've done all I could do. In this case, you will have a rich, metadata export. To stress the fact that nDPI has not been created to intercept people, to extract, data very deeply, but has been created for network visibility. So therefore, what we do, we limit ourselves to information that makes sense from the monitoring standpoint. And we, at the moment, we don't have implemented the callbacks for triggering actions whenever a certain information is reported. So for instance, a URL. The information depends on the type of flows that we are monitoring. So in this case, I'm showing you TLS and Quick. Okay, so we have a lot of information starting from fingerprints to browser heuristics. So we have information about the encrypted traffic and so on. We have other protocols that have no metadata at all. Okay, and we have other protocols that have more limited metadata. So therefore, what I want to say is that this metadata, okay, depends on the protocol. This one affects the memory that nDPI is using. So going back to a few slides back, you have seen that when I show you that the memory increases or decreases according to the protocol. And this is the reason why, okay, the memory is different, simply because we have more data for some protocol and less data for other protocols. In order to speed up detection, and also in order to detect specific protocols, we need to rely on caching. Okay, that's a very relevant technique inside nDPI. And this happens, for instance, depending on the protocol. There is not a rule of thumb. So in case of BitTorrent or Microsoft Teams, for instance, we need to keep in memory, so in this case, into a cache, information about the protocol. Or imagine a simple protocol such as FTP. Okay, when you start an FTP communication, the first thing you do is you open the command channel So where you connect to the server, you authenticate yourself, and you start moving files, get or put, right? So the get or put files are communications that have been started by the command flow, and that don't have anything special, simply because they contain just the file that you're moving. That can be, a picture, can be a binary file, can be a text file, anything like that. And the same happens with other type of protocols, such as BitTorrent or, for instance, Microsoft Teams. So in essence, whenever we see those protocols that, by nature require some sort of caching, so some sort of storage of information for ongoing communications, we save this data, and this data is saved into something called LRU, least recently used. So it's a cache that is filled up with this data, and as soon as we have fresh data that requires room, the older data is automatically removed from memory. So therefore, the memory size of nDPI is somehow constant, and nDPI ignores or forgets, let's say, those that have been observed a while ago. These caches are depending on the protocol. So as you can see here, we have different type of caching. Okay, for instance, we have mining, Microsoft Teams, Signal, this type of caching, and they depend on the protocol. One of the caches that is probably interesting is the one for FPC, that stands for First Packet Classification. The idea here is very simple. We want to reduce the number of packets that we need to dissect for a certain flow. We need to do that because we want to be efficient. If we want to be efficient, we need to be fast. And ideally, we should stop at the first packet. In order to achieve that, so we somehow store some information into a cache so that it allows to detect the future flows, okay, based on past knowledge, FPC. And the use of FPC, of course, is a cache, so it can introduce false positives. But according to our test, this is more a theoretical risk than reality, and it can happen only with CDN, so with hosts that are, let's say, serving multiple protocols all at the same time, because they are shared by users. How FPC work? It works this way. So suppose that you observe this flow, right, from the source IP 192.168.20.13 toward this host ABCD, okay? And this one has been detected by nDPI as GitHub, okay? So this TLS, and on top of which there is GitHub. nDPI, so with FPC, stores in cache the fact that this host ABCD port 443 means TLS GitHub. Because we have communication that by nature, okay, are not unique. So think about HTTP in particular, the old HTTP 1.1. You will see one flow towards the server, and another flow for requesting the images, another flow for something similar. So if you have detected the first flow and it's in the near future, okay, so you detect similar flows from the same source host to the same destination host, the protocol is going to be the same. So therefore, this means that if you enable FPC, because this is a feature that you can enable or disable at runtime, in this case, nDPI will not dissect the traffic, because if it sees in the near future another flow towards the same IP destination and port, it will conclude that this is TLS GitHub without going deep. Okay. If you see nDPI reader, if you start nDPI reader, you will see that it reports both what nDPI said. So this guy is the confidence. DPI means that we have dissected the traffic, and with after 11 packets, so we made the conclusion this was really Zoom, okay, because this is the product TLS Zoom, okay. But FPC says that with one single packet, this was Zoom, okay, and the confidence is the DNS, meaning that so we have relied on the host name in addition to IP and port. Now, this means that most times, okay, you can theoretically reduce the dissection to one packet simply because we use these tricks. It's not, let's say, something that you need to use all the time. You can turn it on or turn it off. By default, it's on. And we believe it's very useful to improve the overall performance. But when a protocol is reported, nDPI has to report the confidence of the dissection, okay? And this is very important, because sometimes there is some data that you can trust 100%. Sometimes it is not probably sure 100% that the protocol is really the one nDPI reports. This is very important because if you have to do things that need to be 100% accurate, okay, it's very important to rely on the accuracy and the confidence. The confidence is another attribute of the flow that specifies how a certain flow has been detected by nDPI. If it says confidence DPI, so it means that the flow has been fully dissected. So we have analyzed the packet, we look at the packet payload, and we believe that this is, really the protocol that we are reporting. So we're confident. I don't want to say 100%, but we have done our best unless there is a bug. So the confidence is close to 100%. Instead, if we use first packet classification, or if you use a cache to report that, or if you use the IP address, okay, to classify a certain flow, might be that the confidence is not that high. So when you have, look at this picture, when you have the protocol, you will always have to look at the confidence. Confidence is an important metric that is used to report you when a certain flow is detected, what type of confidence you can have on the library. If it's DPI, I don't want to say 100%, but you're close to 100% accuracy that this is the real protocol. If you use some other aggressive techniques, so for instance, DPI aggressive used for OpenDPI, this is likely to be correct, but we cannot guarantee 100% that it's like that. And the confidence and the heuristics are two things that go together. For instance, one of the recent trends in this industry is to have somehow privacy VPNs. So those VPNs you can find on Google Play, on Apple Store, that you install on your telephone. You can connect anywhere in the world, and they're supposed to guarantee you privacy and the fact that you are not being intercepted by the ISP or the network provider. And those most, I don't want to say all, but most of them are somehow derivative version of OpenVPN, sorry. And an example, for instance, is NordVPN, that is somehow OpenVPN with some differences. We have implemented a technique that was documented in a paper to detect those VPNs that theoretically are untrackable, but in practice they are. But in this case, we use some heuristics, similar to what we do with BitTorrent. So in this case, when we see confidence, okay, we believe that this is the protocol because we say, okay, this is what we think it is, but you have to pay attention to the confidence. That is very important. If you have a network administrator, if you want to block this traffic, you need to make sure that you are 100% sure that this is the real protocol. Or if I'm sure, probably you better divert this traffic on a VLAN with some sort of different type of checks, okay, lighter checks, but that is not in and out. When you define a custom protocol in nDPI, of course, you can write a custom dissector. It has to be written in C. This is not what many people want to do, okay, because we are not all developers. But this is the way it works, okay, so it has to be written in C. However, sometimes this is not necessary because you already know the protocol in advance and you are not an expert of analyzing traffic, okay? So, but if you say, this is a PLC or this is a mainframe, and I know for sure that this protocol, for instance, it's a certain proprietary protocol of my PLC manufacturer, you don't have to spend time creating a dissector or coding it, asking for some consultancy for doing that. But you can classify that by yourself and define it in a file. So for instance, if you go under examples, you will see there is a file called protos.txt that contains the definition of protocols. Let's take some example. So you can define, for instance, here at the beginning, some protocol based on the port. So if you say TCP and port, whatever, so this is the protocol. Or you can specify also the host. So if you say TCP or UDP or IP, in this case, I'll look at this one. If you see this IP, so it means this custom protocol. Or if you can say, if it matches this particular BPF-like expression, say host this and port whatever, then this protocol. Or you can specify other type of rules based on the host name. So for instance, this is a rule for Disney Plus. So you specify if the host name ends with this or ends with this, then this is Disney Plus. Okay. They don't require coding. You simply have to respect the format. You have to specify, for instance, in this case, the layer 4 protocol TCP, double colon port, and specify at protocol name that you like. Okay, and you can eventually also add an ID to this protocol. This is an example. It's equal, okay, protocol ID. Okay, very simple. You can reload it at runtime. As I've said at the beginning, we are tackling visibility. Okay, and today one very important argument in visibility is cybersecurity, because people want to understand whether the networks are secure or not. And we don't want to create signatures such as Norton Suricata, because otherwise everything will run out of control, simply because we'll have a major performance overhead. We need to constantly check, signature to create signature. So this is a business we don't like. So what we want to do is we want to report cyber risks based on facts. So during that section, we detect things that are not what we expect to see, and that can be useful to AI applications, that are those applications that through AI try to make to have an idea of what is happening on a network, and to create, let's say, a report, or trigger an alert based on that. And this is called flow risk. A flow risk are about 50 indicators of issues that we have found on the traffic while dissecting it. As you can see here, I painted in different colors. Black means clear text only, red encrypted only, or blue both clear or encrypted text. And as you can see, we discovered simple issues such as TLS certificate mismatch or certificate expired, or for instance we have obfuscated traffic. Obfuscated traffic means that this is a traffic that is not encrypted, but it's obfuscated. Means that naturally, so we are able to detect encrypted traffic because of the entropy. Okay, because the way it is represented in packet payload is typical of encryption. Okay, encryption doesn't mean that everything is completely not understandable, because I've said at the beginning, there is a part where we have some sort of negotiation, but forget it for a second. The rest of the flow, okay, is encrypted, means that we have an high entropy. If the traffic looks too much encrypted, okay, this is very strange. Okay, it doesn't look like a real encryption. Okay, this is the typical way that those kind of VPN based on OpenVPN are working. So they try to encrypt, then they try to obfuscate the traffic. So these are risks that we report on the traffic. For every risk, we give a score, an indicator of how dangerous is a certain problem. Okay, and based on that, you can create application or rules that will trigger alerts whenever something wrong happens. This is what we do, for instance, with ntop NG with flow risks. However, okay, in real life, we also have some exceptions. So for instance, you have an old device, an old printer sitting on your network that we all know that is insecure, that is full of bugs and everything, but that we want to replace, or we cannot replace. Okay, this is because the printer is very well protected through access control lists, for instance. So we are not we are good. Okay, we are confident that this is not going to create us problems. So we need to create an exception, because otherwise nDPI will trigger over and over those flow risk alerts, okay, even though they are not alerts, because we detect, we believe that those are not very relevant. So inside the same file, you can specify something called risk mask that masks for a certain IP or for a certain set of hosts a certain risk. Okay, you can say mask everything, so put equals 0. So 0 is the mask, so it means hide all the risks. So this device is safe. You can also specify some certificates that, even though they are not trusted by everybody, for us are acceptable, because for instance, the certificate that we have on our network. Putting this on the Protos.txt allows you to avoid nDPI to generate those alerts. And to make this, to report this in a picture, you can see this is an ntop NG. So if you have attended the previous webinar, you have seen this picture that looks familiar to you. You will see that all this data is reported in our applications. Okay, and you will see that this information is coming from nDPI. And we also have embedded inside nDPI third-party sources. So for instance, in this case here at the top, you will see that this is a malware. Why is a malware? Because we have seen that the destination IP address belongs to this list, Subsphere Lab list, protocol list. It's a block list. And nDPI has loaded this data. Okay, we have instructed how to do that. And put this one inside the library, and thanks to that, we have labeled this traffic as malicious simply because of that. So this is the big picture in essence at the end of nDPI. One of the latest things that we have developed last year is support for fingerprints. If you have attended some of our webinars, you will see that we are now playing a lot with those fingerprints because we believe it's an interesting method for knowing more, okay, than what you can imagine out of your network. For instance, the fingerprints are used to identify devices. A typical fingerprint is DHCP fingerprint. So when a host connects to a network, the first thing it does starts to acquire an IP address, and the way it requests the IP address can be easily used for detecting whether this is a machine running Windows, macOS, or Linux, just to give an example. Type of fingerprints rely on other type of information, such as the user agent, for instance. And if you see also the host names that are accessed by a device when it connects to the network, for instance, most devices today want to figure out whether they are connected to an open network or to a closed network that is blocked by somebody. So in this case, these are typical think different.us site accessed by an iOS device right after the connection, or connectivity check.android.com is the one used by other devices. Or for instance, you see, Firefox settings or services.mozilla.com. Okay, this is a typical indicator for saying that this is Firefox that is doing this traffic. Okay. And fingerprinting for us, it's a big argument. So we have many fingerprints. I don't have enough time for going deep into all those fingerprints, but they are supported by nDPI. What I wanted to say tonight is the following: that we have included inside nDPI a small database of fingerprints, okay, that are enough for us for detecting big families. I mean, we divide the host into families. So I will not tell you if I'm running Android 12 or Android 14. Okay, this is not possible. But I'm going to tell you whether this is an iPad or an iOS phone. Okay, so this is what I wanted to say, and it's very important because we can have additional indicators. For instance, for detecting a situation such as an hotspot. Okay, if you have an hotspot, you will probably see multiple operating systems, with the same IP address, or multiple fingerprints with the same IP address, even though there are other means. So for the TTL, that is the case by one. So thanks to fingerprints, we can detect some operating system, for instance, or we can also work at an upper layer for detecting fingerprinting of applications. Okay, fingerprints are not unique; they are indicators. Okay, don't forget that. But if you combine all of them, for the TCP with the JA4, that is the indicator used for TLS and QUIC, you can have a very good way of having detection of, for instance, malicious application running on your network, or for detecting other type of application that we'll be showing in a second. Let's say also that we want to fix another problem, anticipate a problem. So today, if you are running an open network, or if you have machines on the internet, you will see that many times they are scanned by remote applications that are looking for services because simply they want to break the security. And a popular way of scanning very fast is to use two tools. One is called ZMAP, the other one is mass scan. And if you look at those packets, for instance, you see that inside those packets there is something missing. These are SYN packets. Okay, the first packet that is sent to connect to a TCP service. As you can see here, there are no TCP options at all. Okay, so these are the typical example of an application that is not generating packets based on a TCP stack, but tries to generate the traffic as fast as possible, simply because they want to scan the internet in seconds. Okay. nDPI is able to detect that, but nDPI is also able to tell you that this fingerprint is not normal. Okay, it's special. It's crafted. Okay, so this means that when you receive this packet from a certain host, and the first packet you will see this one, you can safely drop this host, not this communication, simply the host, simply because this is a scanner. So this is an example of how fingerprinting is working. And now what we are doing, we are clustering data according to fingerprints, and we're clustering domain names according to fingerprints, just to understand also what type of flows are generated by a certain application. So in this case, for instance, TikTok CDN, as you can see, okay, they have those names. But because you are a human, you know that what is TikTok, that it's a social network, right? So we would like to do it in a more automated way. So what we are doing, okay, this is an experiment. So we are creating our testing environment. So we are scanning the internet, so crawling the internet to extract data out of our domain name. So for instance, tiktok.com. We download the data, we classify this with a GPU, with a large language model, and we report, okay, the type or the description of a certain site. So in essence, this is the picture. So we have created a web scraper that is downloading, is scraping the internet, not all the domain names, because that would be too much, but the most popular ones. At the moment, again, this is an experiment. So we are using the nTop cloud to collect from specific nTop instances to which we have the consent to know what domain names are accessed. And thanks to that, through an LLM, through a GPU, we classify this into categories. And there are the categories that we have inside the nDPI. And we store this into a domain database. The idea that at some point we would like to offer with nDPI this database, so that not only you know the protocol, but you also know the type of traffic that you have on your network. Actually, we would like to do something more. And I let Francesca, that is a student of mine, to explain what we are doing in this respect. Francesca, please jump on stage.
Hi. I will talk about this way of generating in a semi-automatic way some fingerprints. This is still a work in progress, but the main goals are to, given a network, for example, to check which apps are running on the devices connected to the network, and to check if they are unexpected apps or unknown, to check if there are apps installed on some business devices that have no authorization to be installed. But also one goal is to cluster the flows, so to group together the application and to remove the background noise, for example, that is given from the traffic generated by the OS of the device. And this can also be done. This can also be useful to classify together the application and to check if the application is connected to some harmful IP, for example, and so to detect the harmful traffic. The aim is to create some fingerprints in a way that is semi-automatic. So this means that there is less needed interaction from the end user of nDPI and to be integrated into nDPI. The fingerprints that are used are the same that I've mentioned before, and they are the GA4 fingerprints. Only the last two parts of the GA4 are used, and these parts are related to the software suites of TLS, the extensions, and the signature algorithm. In the original GA4, these are hashed using SHA 2056. But in the work I'm doing, I'm considering them in their unsorted, unhashed version in order to have more granularity to classify the applications. And this is done as of today only for traffic that uses TLS and QUIC in order to have this TLS information. What I'm doing is I use the nDPI reader tool that, given a pickup file, is able to generate a JSON file containing some information and grouping together the traffic as flows. This information can be, for example, the IP address contacted and the port, but also information on the protocols. I'm then looking at the JSON file generated, and I'm extracting from it some useful information, for example, the TCP fingerprint and the GA4 fingerprint that I use in their unsorted version. And I also look at the host name. This information are used to be filtered, and I remove all the host name that are background noise, for example, that are contacted by the OS and they are not related to any app. And the current output of this system is to associate a single JA4 unsorted with a list of app names that have .JA4, and on the other hand, to have for a single app name the list of all the fingerprints in a JA4 unsorted form. Then the current work is only considering pickup files that are generated from mobile devices, and these mobile devices have different versions of Android and iOS systems. The result obtained right now are that I have 33 different JA4 unsorted, and only 7 of them are shared among different apps. This means that 25 of them are unique and can be used for classificate the apps. For example, if I see a JA4 that is only used by YouTube, for example, I can know for sure that that device is running YouTube on it. Some things that I've noticed are that there are some shared JA4 among the apps. This means that I can't use this kind of information to be sure about a certain apps, and so I will look at the host names, and the final goal is to only have one JA4 associated with a single app. And also one other thing to do in this work in progress is to check the contacted host name to see if that host name is harmful, or is separation is okay or not.
Okay, thank you, Francesca. This is an ongoing work that we plan to complete this year, that we believe will be relevant for simplifying the way nDPI works and for automatically classifying or semi-automatic classifying traffic. nDPI can also be used as a lightly weighted IDS. Okay, in nDPI you can export data in JSON format. So for this is an example. As you can see here, we're exporting as much information as possible. So in a way, this is similar to what you have with other popular IDSs, but with DPI. Now, this is very important because many IDSs are relying on signatures. Okay, here we don't rely on signature. And combining these two types of data, the source of data, I think is very important, okay, for having, let's say, a complete understanding of the traffic without being too heavy, because here we don't have the need to know rule by rule what is happening, therefore overweighting the application. That's why it's lightweighted. nDPI can be used not only to monitor traffic, because this was the initial need, but also to enforce traffic policies. A typical example is that you want to block scanners, you know, I've shown you before an example, or you want to block specific protocols, or you want to block trackers. So, you know, for whatever reason you want to say, okay, this protocol can flow, this protocol cannot flow because this is not a business protocol, for instance. And therefore, we need to be able to combine this with blocking. We have implemented this in some applications. So we have ntop Edge on nprobe APS that is doing that. But soon we'll be introducing a new tool that's a traffic enforcer for Linux. So in essence, it's an application that relies on NetFilter that is pretty simple in nature. As you can see, the configuration is very simple. So in blue, you will see two parts, okay, that extract the NetFilter to remember for a certain flow marker. The marker is an ID that is attached to a flow that says what we should do with that flow. So it basically says whether that flow should pass, should be dropped, or should be passed but very slow. In nDPI, in essence, we have no ability of running into the Linux kernel. Actually, this was one of the features available years ago, but we believe that was not a good idea, so we have removed. Now there is a new mechanism called NFQ that allows to send packets to user space to one application called NFW that is running on user space that receives the traffic and decides what the traffic is going to be, sets a marker, and based on the marker, the kernel will honor that. So it means that after the first few packets, the flow is detected. If the flow is detected, then future packets don't have to go to user space anymore. So in essence, this way we are able to label traffic, we are able to set the protocol on a traffic flow, and based on that, so we can block traffic or we can promote traffic or prioritize traffic based on the content and not based on the IP. This is one of the next things that we've been doing this summer. And of course, we are an open source project. We want to, we want to be integrated with other open source projects. The two projects that are using nDPI that at the moment we have somehow coded ourselves is one plugin for Suricata DS. And also, it's another extension for Wireshark. If you remember at the beginning of this presentation, I've shown you that there is a folder that contains Wireshark data. Okay, this is a Lua script used by Wireshark for dissecting traffic, because Wireshark is focusing on packets, on things such as transmission, latency, typical network metrics. But with nDPI, we can know more. We can combine the power of Wireshark with the knowledge of nDPI. As I said at the beginning, nDPI is much more than just a DPI toolkit. It's a library that provides a basic layer on top of which a monitoring application or networking application can sit on. These are some of the algorithms that are implemented by this library. So you can imagine that there are many more. We don't have time today to cover all of them, but I suggest you to look at the library from the developer standpoint if you need to implement some algorithms that are useful for you in your daily routines. So for instance, for comparing data, for doing unsupervised machine learning, for looking at IP in radix trees and so on. So they are all part of nDPI and they are free of charge. Before we wrap up, I want to spend a little bit of time on testing. Testing is very important. We believe that testing is one of the core activities simply because without testing, you cannot rely on the library. We are part of the Google continuous code fuzzing. Okay, so it means that every night Google spawns some containers that stress our code just to figure out whether there are some bugs. Okay, this is something that does all the times. Okay, automatically in the background and reports us bugs that we try to fix as fast as possible. We also have inside the nDPI, there is inside the test pickup folder, many pickups that are used for regression testing. So whenever we change something, we want to make sure that we have not broken anything else. And those pickups are also used by many other open source projects to test their tools and to somehow to test whether what we are doing makes sense or not. And they're used for regression. In particular, we also have GitHub testing. With GitHub means that whenever we commit a change to the repository, we have some actions that are automatically executed. And those actions simply download the code, try to compile the code on multiple platforms, on platforms that we have no idea, how to access, such as an IBM mainframe, for instance. These are typical platforms that we support. And on those platforms, it runs some tests, fuzzy test or other type of test using the pickups that I've shown you before that are part of the test pickup directory, part of nDPI. So therefore, whenever we commit the code, GitHub is doing some tests, and overnight, every night, Google is performing continuous tests on our code, trying to break it and trying to make to spot bugs, okay, that you should not encounter. And this is very important because that makes this code pretty robust. Just to give you a quick outlook of what is our roadmap. Okay, first of all, this summer we'll be releasing this NFW, so this firewall-based application for Linux, the one used in nDPI. As I said, we are creating a classification platform for classifying domain names, for dividing them into categories. At the moment, this is just an internal project. It's under development. We are using LLMs and GPUs, but it's something that we would like to release at some point so that we can combine this with the power of nDPI. So therefore, when we have a category, we don't want to report simply web, but we want to report, travel, business, bank, things like that. At the same time, we are used by many people in cybersecurity, so we want to create some block lists. Okay, so there are many block lists available on the internet, but because our software is popular, so there are many users that are using it on the internet. Also, we need to use it for running our own services. So we have created somehow a distributed system that allows us to detect what is happening and to protect ourselves. Okay, using that, we are thinking to create a block list to be distributed to a user base, so that it's a timely block list. But contrary to other block lists that are downloaded and installed into routers, from time to time, let's say once a day or once every 12 hours, we want this to be dynamic. So we want to create a sort of continuous stream of data, okay, so that whenever there is somebody that is blocked, let's say in Europe, okay, this information is also notified in South America immediately, so that when this scanner, you have seen that we have mass scan and zoom map that are able to scan the internet in seconds, whenever this guy is talking with other remote host, it is immediately notified without waiting days or more with usual block list. We are making some experiment with AI. We don't want to use AI inside nDPI. I mean, this is not our plan, but we want to use AI before nDPI. So in essence, how can we solve the problem that somehow Francesca is also tackling? So in essence, how can we use modern techniques, okay, to simplify the creation of new dissectors, or to use nDPI in a way so that the traffic can be detected without talking with experts, okay? So this is something that, it's a bit challenging, but we are confident that we can do it. And then at the end, I want to say that for a long time, we had in mind to create something that we call internally nDPI plans. So let's say an extended version of nDPI with custom features for OEMs and for system integrators. We are unsure whether this makes sense or not. So, having a feedback, that would be great. And just to conclude, those who like nDPI are free to attend this webinar that we are organizing with an Italian company called FlashStat. FlashStat is a company that is classifying domain names. It offers a classification service for domain names. And the idea is to talk about nDPI and to see where this can be combined with classification, okay, similar to what I've shown you before, but in more massive, so that we can include in nDPI the ability of classifying domain names extensively. Okay, so we'll be discussing that in this webinar, and we are looking for feedback. I want to thank you very much, and now I open the stage to questions. So if you have questions that you want to ask about, roadmap, things that are unclear or whatever, just open your microphone or write in the chat, and I'll be open to answer.
Luca, there are a couple of questions in the Q&A section on Teams.
Okay, please.
So I don't know if they want to open the microphone and ask, maybe it would be better. So there is Fred from Vodacom. Do you want to ask your question?
Oh, yes, thanks, Luca, for the session. I was just wondering if nDPI is the foundation of all your tools, so could we, for example, develop our own tools based on nDPI and use the information that it has available?
Yes, definitely. This is the case. There are many companies that are using nDPI that are not, involved with nTop, that are using our tools. There are many small home routers that are using nDPI. Yes, the answer is yes. So if you go inside OpenWRT, that's a popular project, for instance, for small routers, for CPE, you will find the library. Yes, you can develop your own library.
Okay, thank you.
Welcome.
And then we have Mohammed asking about nDPI used for bridging the traffic. Mohammed, do you want to talk?
Bridging is definitely possible. Okay, so if you have Linux, you can do that with the bridge, and you can apply the same technique I've shown you before. Yeah, to be releasing this one. So in essence, whenever there is a flow that has to be bridged across 2 or multiple interfaces, the flow will go to user space. The first few packets will go to user space. nDPI will detect it. And based on that, you can decide whether you want to forward it or not. This is not an on and off, okay? So of course, you can also use the traffic controller, the shaper inside the Linux to reduce the speed of selected flows. So yes, this is possible. And in addition to that, we have a high-speed tools, for example, nprop cento, that can do that at 100 gigabit. But again, you can create your own library, your own application. I'm showing you that the code is pretty simple. And just a few calls to make. Go back to the slide. Yeah, it's very simple. So for every flow, you simply call detection process, and as soon as you have the proto ID returned, you're done. You can just decide what to do. Inside the example directory, there are also some tools based on DPDK. That's another popular capture framework that you use as an example. So if you want to see how to do that.
Yeah, we also have PFRingFT, which is based on nDPI that simplifies the development of an application like this.
Exactly. Other questions, Alfredo?
No, I don't see other questions. So I think we are good.
Okay, guys, we'll be sharing this video on YouTube. We'll put this video on our blog. Thank you for attending it, and I would like to hear your feedback. So if you want to send us an email or send us a message on Discord or Telegram on our groups, that would be great, because we would like to know where to go. Okay, what are the next steps? Okay, and your feedback would be very valuable. Thank you very much for attending this event. See you soon.